chapter 7, the first two exercises we did. I had you do the poker chip exercise, and then I had you do the class heights exercise. And I did it on purpose because I want you to understand the first exercise was based on you drew poker chips, and you counted how many you had, but then you calculated what percentage you had red, what percentage blue, green, white, etc. And then the heights. You sampled 4 students at a time from my list, if you were here, and then you calculated the mean of those heights. I want you to understand that what we're doing in chapter 7, there's going to be 2 sets of rules. There's going to be a set of rules that you use for percentages or proportions, and then there's going to be a set of rules that you use for means. So we did proportions, now we're going to do means, okay? And I'm emphasizing this because I'm telling you, every year what happens is people have the general idea of the concept, but they use the formulas for proportions and percentages. They try to use those for the means and vice versa. Okay, the rules, there's overlap. We could make a Venn diagram of it. There's some things that are similar, but then there's some things that are very separate, very different. So this example is based on means. And I am on page 10 of your notes packet. And it says, in the last section, we learned that the mean of proportions calculated from repeated samples can be used to estimate a population proportion. In other words, mu sub p hat is equal to p. But now what we want to do is decide how good is mu sub x bar, which is the mean of the means, how good is that to estimate the population mu? So this applet is from the same website that I got the Reese's Pieces one, but this one is based on words in a document. And I chose, this one is the Gettysburg Address, okay? So someone put this whole thing together, population size, there are 268 words in the Gettysburg Address. And you guys know it, 4 and 7 years ago. Yeah, oh, well, it's not hard to learn. But anyways, I used to know it. But what someone did, and there's a lot of information that we're not using here, but we're going to use every word, the length is 4 letters. Say this one is 5, this one is 3. And so someone put this applet together, and what it's going to do is it's going to draw one sample, and it's going to draw a sample size of 10. So it's going to pick 10 words out of the Gettysburg Address, and it's going to calculate the mean of those 10 words in terms of its word length. Okay, so let's do draw samples. All right, so down here, and this is actually, I'll explain on the handout, but this over here, this is the population data, okay? The mean of the population. Now understand, in real statistical life, that's what we don't usually know. We don't know the population mean. We don't know the population standard deviation. We use the samples to estimate it. This is artificial. This is us knowing about the population and confirming that this process actually is valid, okay? So the average length of a word in the Gettysburg Address is 4.295, about 4.3. The standard deviation is 2.119. This one sample, right here, that's what that one sample looks like. It came out with a mean of 3.9. Okay, that's what I actually had you putting on that first blank there, 3.9. And it came in with a standard deviation of 2.183. And I don't know if you noticed this, but these dots right here, those are the 10 dots. But they also show you in your population where those 10 dots came in. So you can kind of compare it to the population. It's kind of a cool feature of this app. But I want you to notice we have a clear right skew on this population. I chose this for a reason. I wanted to start with something that was skewed. Okay, so that kind of just shows you what this is doing. I'm going to do a reset. And what I'm going to do is we're one sample. That's not repeated sampling. So we're going to get rid of one, and we're going to do 500. Okay, get rid of the one. We're going to make this 500. Let's see if that works. Beautiful. So it's going to draw 10 words, calculate the mean, plot it on the graph. 10 more words, calculate the mean, plot it on the graph. And it's going to do it 500 times. Okay, here we go. Draw. All right, what this picture is, this is the most recent sample. So that was number 500. This is our approximate sampling distribution. Okay, so in our chart, when n was 10, our mu came in at 4.298. So let's write that down in our table. Our sigma came in at 0.657. And we need a shape of this distribution. What do you think? It kind of looks approximately normal. Okay, the bottom line is if somebody walked in, one of my AP staff students from last year walked in, I think they'd probably say approximately normal. But could you actually see that there still is a kind of a slight right skew to this? Okay, that was the reason I started with this Gettysburg Address examples. I wanted you to see that if you start with a skewed distribution, the sampling distribution may still come in with that slight skew, but it's definitely not as severe as the original, right? Okay, we're going to do a reset, and we're going to leave the 500, but I'm going to change the sample size. We're going to go bigger. We're going to go to 50. So let's get rid of the 10 and make it a 50. And draw. All right, this mean came in at 4.283. This standard deviation came in at 0.256. And this one also is approximately normal for a shape. So you can see, hopefully already, some of the similarities from what we did last week with population proportions. Do you see the standard deviation started out at 2.1, but now the first sample came in at 0.6 for the standard deviation, then it came in at 0.2. What do you think is going to happen on this one? It's going to get smaller. All right, so let's get rid of that 50. Let's go with n equal 100. Oh, no. Delete. 100. Because I didn't realign my board. Okay, here we go. Now, I actually like this, and we would go with an n size that's as large as this one. Look at the most recent sample. Do you see how the sample still kind of looks like the population? Okay, but with repeated sampling, now your approximate sampling distribution comes in approximately normal. All right, and that last one, we have a mean of 4.283, same as before, and a standard deviation of 0.168, a little bit smaller as we would have guessed, okay? And just like what we did last week, what we're going to do now is we're going to derive a formula that instead of just saying that as the n size gets bigger, sigma gets smaller, we're going to come up with a formula that would tell us how much smaller. Yeah, we need to know exactly how much smaller. All right, so we're done with the app. All right. Summary statements. The sampling distribution, now remember, I'm not going to keep writing this, but we are actually considering the approximate sampling distribution, okay, because ours had 500 dots. The real one has a lot more. But the sampling distribution will be approximately normal if the sample size is large enough. And we will discuss what large enough means at another time. The center, the mean of the sampling distribution, that's your mu sub x bar, will be an unbiased estimator of the population mean mu. Okay, so remember, if I go back to this was artificial. We knew the population standard deviation. We knew the population mean was 4.295. You have to understand, in the real world of statistics, that's what we usually don't know. But hopefully from doing this, you would agree that even if we didn't know mu was 4.3, could you have estimated 4.3? Yeah, every single time. Okay. Now, we also wouldn't necessarily know 2.119. And if these keep changing, how are we supposed to use these to estimate 2.119? Well, that's the formula that we're now going to derive. Larger sample sizes will reduce variation, but now let's talk about reduced variation, specifically how much. Okay, so I totally bungled this last hour because I did what I told you guys I have done every year I've taught this class. I confused my combining random variables with transforming. Oh, I do it all the time. Okay, so let's go back and review a couple things from chapter 6 so I don't make the same mistake. So in our example, we were collecting words from the Gettysburg Address, and that would be a random variable because every time you select a different word, it could have a different length, okay? So the total number of letters would be how many letters did we get the first time, plus how many letters did we get the second time, plus et cetera, et cetera, et cetera, and up to however many. But each one of those is a random variable. So this is like the apple example in the notes from chapter 6. So this is combining individual random variables. So if I wanted to figure out mu sub t, I could take mu sub x1 plus mu sub x2 plus et cetera, and it would just so turn out because they all came from the same population, they all had the same mu, so there would just be n of the mu sub x's. That formula is the same whether you're transforming or combining, but we have to keep track. I have to keep track that right now I'm combining random variables. So if I wanted to do sigma sub t, I can't add sigmas. I have to add, all right, sigma squared for x1 plus sigma squared for x2 plus et cetera, up to sigma squared sub xn. And to get it back to standard deviation, I would have to take the square root of that. So this turned into, we would have n sigma squareds for x, and then they would be square rooted. All right. Now, if we think about what was happening every time we took a sample there, or when you did the class heights, okay, if you were here that day, you drew 4 students from my list. You added up their heights, and you divided by 4 because you picked 4 students. That's how you found the average. So in this case, the computer was selecting 10 words from the Gettysburg Address. It added up however many letters, divided by 10 to get the average. So in summary, we could say that the average word length was the first word length plus the second word length plus et cetera, up to the nth word length. Now ours was 10, but add them all up and you would have to divide by your n size. But with a little bit of substitution here, all those x's added up, I defined as t, the total number of letters. So I could call this t over n, or better yet, I could call that 1 over n times t. Now, up here, this was combining a random variable, but down here, this is transforming a random variable. So t is created by taking a whole bunch of x's and adding them together, but now t is being transformed into x bar by multiplying by 1 over n. All right, so transforming a random variable says, if I want to get the mu for this new one called x bar, mu sub x bar would be equal to 1 over n times the mu for t. But with a little bit of substitution, the mu for t can be substituted. So we get 1 over n times mu sub x, and the n's cancel. And we have algebraically established why mu sub x bar should give us mu for the population. It's pretty amazing, really. Now, remember, we're now transforming. This is when I realized what I had done, because when I did my substitution, I'm like, this is not right. But now I'm transforming. So if I want sigma for x bar, now when you're transforming a random variable, you really can just change the sigma. So I could take 1 over n and multiply by the sigma for t. But sigma for t is going to get substituted with that. So that will become 1 over n times the square root of n times the square root of sigma squared sub x. Now notice what I did with that square root up here. I had the n and the sigma squared all underneath one radical. I broke it apart. I gave them each their own radical. This and this are identical. But now, if I simplify the square root of n over n, that would equal a square root of n on the bottom. And the square root of sigma squared is just sigma. And there's your new formula. That is the pattern that the sigmas follow as the n size gets larger. Now, can you picture just algebraically as n gets bigger, the denominator is getting bigger, so the entire value will get smaller. Okay, now, again, back to this artificial, because we wouldn't necessarily know 2.119, but let's say we did. Let's see what happens. If I took that 2.119 and divided by the square root of the first n size, or 2.119 I divide by the square root of the next n size, or 2.119 I divide by the square root of that n size, do they work? Do they come close? 2.119 divided by the square root of 10, 0.670. Not bad. What about divided by the square root of 50? 0.3? Square root of 100, better known as 10, by the way, 0.2119. Yeah. Sampling variability. Yeah. Now, remember, this is normally in reverse, okay? Because normally we don't know sigma. We would get these values from our sample, but if you have a formula that the sampling standard deviation should equal the population divided by the square root of your n size, you could use algebra and you could solve for sigma sub x. Okay, that's how it's more typically used. Okay, all right, so this is the summary right here. This formula for your mean and this formula for your standard deviation, they are on your formula page. Okay, they're on the formula page. But remember, you still have to satisfy your 10% condition. You still have to make sure the 10% condition is your independent condition. This is the one the College Board calls your large population size. They kind of think of it in reverse. They say your population better be so large that it means your sample has to be less than 10%. Okay? Now, what I want to point out that's not here is the normal condition. And if I flip back to what we did last week, remember these formulas that I said you need to memorize because they're not on the formula page? See, the kicker is, you see what letter that has there? P stands for not probability here, not parameter here. It stood for proportion or percentage here. I actually don't like that. The letter P is used in so many different ways. In this formula, P is your success proportion. So if you said probability, you probably were thinking along the correct lines. But this went back to like if it was a 75-25 split. That P is your 75 versus 1 minus 75 is 25%. Those formulas are only appropriate if you're dealing with percents. As soon as we start dealing with means, you should not even be thinking about N times P. It should be nowhere near your paper. And every year I have people, they start crisscrossing the formulas. They have a formula that has proportions and they somehow, it's like, where did you get a percentage to put into that formula? We're dealing with means. Where did you even find a percentage? Okay. These facts about the mean and standard deviation are true no matter what shape the population distribution has. And I did that on purpose also. That's why I chose, that app had a drop-down menu, you could choose different distributions. I chose one on purpose that was skewed because I wanted you to understand this works even if the population is skewed. Your sampling distribution is going to come in approximately normal. Okay? All right. Suppose that the number of movies viewed in the last year by high school students has a mean of 19.3. Okay, so that's a population parameter, 19.3 movies. The standard deviation was 15.8 movies. That's population. Let's say we took a sample of 100 students. That would be our little n size. That's our sample. What is our capital N? What is our population here? High school students. High school. In your building, in your district, in your state, in your country. Do they just said high school students. All right. We'll come back to that. What is the mean of your sampling distribution? All right. I actually want to emphasize that all of those fancy words right there, that's mu sub x bar, the mean of the means. If you made a sampling distribution and everyone calculated their own mean from their sample and they all put it on the same graph, and then we took the mean from that graph, that's what that is. And that should be able to be used to estimate mu. But in this case, we know that, so 19.3. And again, that's in reverse of the way it normally is. Normally, we don't know mu, and we use mu sub x bar to estimate mu. Is the 10% condition satisfied? What the College Board calls your large population size. Is our population large enough to ensure that our sample is less than 10%? Okay. What I would expect to see on your test, you're going to take 10 for 10%. I want you to multiply by little n, 100. And I want you to ask yourself, are we under, at that point, did we sample less than 10% of our entire population? Can we safely assume that there are less than 1,000 people, or excuse me, more than 1,000 people in our population? Yeah. I think we can assume that. Our population is greater than 1,000. Okay. Can safely assume more than 1,000 high school students in this population? I will be looking for two things on your test: the calculation and the explanation. Don't just show me that 10 times 100 is 1,000 and say that's less than capital N. Tell me why we care. We are trying to make sure that our population is large enough that our sample did not violate that 10% condition. Because you have to understand, as soon as we draw one high school student from the population, did we just change the probability that someone else gets selected? We did, but we changed it so minutely that it doesn't matter. Okay, so now that we know that for sure, we are now allowed to do the standard deviation calculation. So the standard deviation of the sampling distribution, now all of that stuff, by the way, sigma sub x bar, that's the symbol for all those fancy words. Sigma sub x bar would be the 15.8 from the population divided by the square root of the n size, which is 10, and dividing by 10 is not going to do anything more than move the decimal, so 1.58. I'm going to say it one more time. You understand that's actually in reverse of the way a statistician would typically do this? Okay. The statistician would do the sampling process and get this answer, and then they would multiply by the square root of 100 to come back to their estimate for the population standard deviation. All right. So I already said these formulas work regardless of what shape the population distribution has. Now, when we looked at the shape of our distributions, we said on all of them that they would be approximately normal for all of our sampling distributions. But I think we agreed even on the first one, there was still a slight skew to that, okay? So what we're gonna talk about through the rest of these notes, I'm not gonna do it all today, but we're gonna talk about how will you know what shape we're dealing with, okay? So I'm gonna start super easy. Rule number one. If your population is normal, which ours wasn't, but if it was, you can automatically assume that your sampling distributions will be approximately normal. That's the easy one. It makes sense. If you start normal, when you take samples, you're going to end normal. Now, I'm not going to take the time to go through the applet, but that's what these diagrams are. This was me. I was back at that same applet, but I chose a different one, okay? I have no idea if it's hours of sleep, okay? So in this case, there were 18,000 individuals in the population. That was a pretty big capital N. They only do 25 samples for this, or I did. But it changed. First, I started N was 5, so a very small sample size. Then I got a little bit bigger, and then a little bit bigger. And that's what all these things are. So this is the population. I think we could agree it's approximately normal. And these keep getting skinnier and skinnier, but I think we can agree that these are also all approximately normal. Because if your population is normal, your sampling distributions are going to be approximately normal. Cool. But they should all have unbiased estimators at the center. So this mean was truly 8 hours. And all of these means came in at about 8. The population had a standard deviation of about 1.5 hours. And these standard deviations kept getting a little bit smaller. As your n size got bigger, your standard deviation got smaller, and they were getting smaller according to this rule. Okay, and you could confirm that you could take on any one of these, you could take the 1.510 and divide by the square root of 5, 1.510 divided by the square root of 10, and then divide by the square root of 25. And they all come out to be pretty close, okay? This diagram, I literally have seen problems on the AP exam that use a different one, but very similar to this. This diagram is showing you what happens to the distribution as your sampling size increases. If your population is approximately normal and your standard deviation gives you a range from here to here, if you start doing a sampling procedure, you will still get a normal distribution, but as your n size increases, the standard deviation decreases. But the area under the curve is always equal to 1. So if the variation is getting smaller, the distribution gets taller. But then if your n size gets bigger, it's going to narrow even more and get even taller. Okay, so I've literally seen problems on the AP exam where they will cover this up and they'll just say, which of those would be the population, which of those would be an n size of 4, which would be an n size of 16 for sampling. And you would just be expected to know the population is the widest one, and as n size gets bigger, they get skinnier and taller. Okay? All right, but if we can be confident that we're dealing with approximate normality, we can do problems with it. Yes. All right, at a peanut company, dry roasted shelled peanuts are placed in jars by a machine. You can kind of picture that going through the assembly line, and some machine is going and just spitting out the peanuts into a jar. Now, the distribution of weights in the jars is approximately normal. All right, that's our population. They are telling us right there, the population is approximately normal. The mean is 16.1 ounces in the population, and our sigma is 0.15 ounces in the population. All right. Now, can you picture if a machine is just spitting out peanuts into a jar? Is every jar going to come out to be exactly 16.1 ounces? Very likely not, okay? Without doing any calculations, which outcome is more likely? Would it be more likely to select one jar and discover that the contents are less than 16 ounces, which is too low? Or is it more likely that you select 10 jars and find that the average is less than 16? All right. I want you to think about it. Okay, sampling variability. Would it be possible that when the peanuts just spit out, that the jar is overfull? So would it be fair to say that it also could be underfull? Would it be fair to say that it might be dead on? Okay, if you only fill one jar, there's going to be a high variability. Okay, because it could come in way too high, way too low, dead on. It could come in all over the place. Call that an n size of 1. But now if we draw 10 jars, you understand now that if you get one jar that's overfull, there could be another one that's underfilled that will balance it out. So which is more likely, getting one jar that's way underfilled or 10 jars that are on average underfilled? The first one. Because on this one, and if you think about it mathematically, on this one, you will end up dividing by the square root of 10 for your n size, and dividing by that is going to give you a smaller variation. Now, we can also prove it mathematically. All right, so we're going to say randomly selecting a single jar is more likely. So now we're going to show mathematically why that works. Calculate the probability of selecting a single jar and finding that the contents weigh less than 16 ounces. All right, so going back to random variables, I'll just say X equals the weight of one jar. So now I want the probability that that weight comes in less than 16 ounces. But hey, they told us this came from a normal distribution, which means I can automatically turn this into a z-score. All right. Now be careful when you think about what I've been trying to really emphasize when you calculate a z-score. You always start with this number right here. That's what you're trying to convert, 16. And you subtract the mean for that variable. So you're going to be subtracting mu sub x, which was given as 16.1. And then you're going to divide by sigma sub x, which was given as 0.15. And I have that comes out to be negative 0.67, negative 2/3. Whip out your calculator, do your normal CDF, and you would get 0.2514, so about 25%. Okay, so you could kind of draw this and you could say, all right, so if z equals 0 is dead center, I have a z-score of negative 0.67, which would be like right about here. You just calculated that whole big tail right there. Okay, so this is the z equals negative 0.67. That's z equals 0. All right, so now calculate the probability of selecting 10 jars and finding that the average content weighs less than 16. So now I'm not going to do the probability that x is less than 16. I'm going to do the probability that the average x bar is less than 16. Now, because the population was a normal distribution, I know the sampling distribution is also approximately normal, so I can still continue with my z-scores here. All right, here we go, though. This is where the new formulas come in. I'm trying to convert the 16. I definitely have to subtract a mu, but this time it's going to be mu sub. Oh, well, that just happens to be the same as 16. It's still 16.1. Okay, because mu sub x and mu sub x bar are the same based on the first formula. But at the bottom, when you have to divide by sigma sub x squared, you don't just divide by 0.15. That 0.15 has to be divided by the square root of 10. And by dividing by that, that's going to change. All right, so when I put this in my calculator, I just put my numerator and denominator in parentheses. You can make a fraction if you want. I just put that in parentheses, and then I put the denominator in parentheses. And I get a z-score this time of negative 2.11. And what that means on your bell-shaped curve, if a z-score of 0 is dead center, you will notice that now we would be way back here with our z-score, and the tail is going to be much tinier. And if you whip out your calculator and do a normal CDF, you would get an answer of about 0.0174. So which is more likely? Yeah, the first one. You have a 25% chance of getting one jar that is at 16 ounces or lower. If you sample 10 jars, you only have a little less than 2% chance. Now, what I'm also going to do tomorrow is, what I want to show you is how this problem, you actually had the capability of answering that same question back in chapter 6. Okay, you have to remember that this formula was derived from transforming random variables. So this was derived from chapter 6 materials, which means this question actually can be answered with chapter 6 content, and I'll show you that tomorrow. But in the meantime, I'm assuming my typo here, if I said doing the odds, I'm assuming I went 49 to 55.
Yeah,
Okay, I'm assuming that's what that's supposed to be. So that's a whopping, what, 4 questions?
Yeah.
Can you handle it?
I don't know. I think, what if there's like A or G for each question?
I don't think it is so.
Oh, that's fine.
So I think you're good.
Thank you, Mr. Barry.
Oh, yeah, the 1.1.